Why do railroads keep building machines that seem to violate every accepted rule of locomotive design? We're counting down 10 of the strangest engines ever constructed, spanning steam, diesel, electric, turbine, and even jet power. Some generated forces their own frames couldn't handle. Others worked brilliantly and still vanished. Each one pushed past what the engineers of its era considered possible, and together they reveal what happens when ambition outruns convention. Number 10 begins in 1914 with a steam locomotive so enormous it could outbreathe its own boiler. In the 10th place, the Erie Railroad introduced a Titan meant to conquer the steep grades of Susquehanna Hill, the Baldwin-built Triplex, Class P1, famously named the Matt H. Shea. Delivered in 1914, this massive machine weighed 853,000 pounds and boasted an unprecedented 28882 wheel arrangement. By placing 3 complete sets of driving wheels under a single boiler, designers aimed for a staggering tractive effort of 176,000 pounds force. But this extreme engineering ran into a hard physical wall. The boiler simply could not generate steam fast enough to feed 6 massive cylinders. Because only half of the exhaust steam went through the smoke box, the firebox lacked the necessary draft, starving the boiler of heat. At anything above walking speed, steam pressure collapsed entirely. Rather than hauling heavy mainline freights, this giant spent its 13-year career relegated to slow helper duties, pushing trains at a crawl before being scrapped in 1929. It proved that raw mechanical power is useless if you cannot keep the fire burning. But if steam had reached its physical limits, what would happen when railroads abandoned coal entirely and turned to the silent, unseen power of massive electric magnets? Number 9 on our list, the Milwaukee Road EP2, known as the Bipolar. Built by General Electric in 1919, this electric passenger locomotive rejected the standard rule of using geared traction motors. Instead, engineers mounted bipolar 2-pole motors directly onto the axles. This gearless design meant the motor armature was the axle itself, eliminating gear wear and creating an incredibly smooth, quiet ride at 90 miles per hour. With 12 powered axles across 3 articulated chassis segments, the bipolar produced 3,200 continuous horsepower. It easily hauled 12-car passenger trains over the steep, rugged Cascade Mountains. Visually, its curved hoods and exposed side frames became a signature of Western electrification. But the elegant direct drive system carried hidden costs. Because the motor weight rested directly on the wheels without springs, the constant pounding wore down axles, track, and wheels at a punishing rate. As maintenance costs climbed, the Milwaukee Road faced the harsh realities of keeping up hundreds of miles of overhead wire. By 1960, the railroad retired the fleet, proving that even a highly successful technical design can fail if the surrounding energy policy shifts. But what happens when a railroad refuses to let go of steam, building a giant that could outmuscle early diesels? 8th place on our list goes to a disciplined rule breaker that refused to yield to the diesel revolution, the Norfolk and Western Y6B. While other railroads rushed to scrap their steam fleets in the 1940s, the Norfolk and Western doubled down on coal, building these massive compound articulated locomotives in their Roanoke shops starting in 1942. This 2882 giant used a 300 pounds per square inch boiler to churn out up to 170,000 pounds of starting tractive effort. To keep its drivers from slipping under this immense torque, engineers bolted 28,000 pounds of lead ballast directly to the frame. The key to its efficiency was compounding, routing high-pressure steam through one set of cylinders before recycling it into a larger set of low-pressure cylinders. This made the Y6B exceptionally efficient at dragging 14,500-ton coal trains over Allegheny grades, though it demanded precise valve balancing and intensive maintenance. Even in a 1952 test against a 4-unit diesel consist, the Y6B practically tied on fuel costs. The class remained in regular service until July 1959, retiring only when diesel economics and the high cost of maintaining specialized steam facilities made coal-based operations untenable. But as steam finally died, what happens when you abandon traditional pistons entirely and build a diesel locomotive with a triangular, aircraft-style heart? Seventh on our list is the British Rail Class 55, universally known as the Deltic. Built by English Electric in 1961 and 1962, this 22-unit fleet tore up the diesel rulebook by using naval patrol boat technology instead of standard prime movers. Inside each body sat 2 Napier Deltic 18-cylinder engines, arranged in a triangular, valveless, opposed piston configuration with 3 crankshafts. This exotic engineering yielded a massive 3,300 horsepower, giving the Deltic an unrivaled power-to-weight ratio that effortlessly propelled heavy expresses between London and Edinburgh at sustained speeds of 100 miles per hour. Crews and onlookers instantly recognized them by their legendary high-pitched exhaust scream. Yet, this high-performance design demanded specialized workshop teams. The complex gear trains and high rotational speeds caused severe maintenance headaches, while heavy lubricating oil consumption ran up operating bills. By 1981, as the more economical intercity 125 high-speed train sets took over, British Rail retired the roaring fleet. But what happens when you attempt to fuse the raw muscle of coal-fired steam with high-voltage electrical generators, creating a sprawling giant that was destined to fail before its luxury train could even carry its first passenger? Number 6 on our list is the Chesapeake and Ohio M1, a machine that looked like a spaceship but worked like an expensive, coal-fired dead end. Built by Baldwin between 1947 and 1948, these 3 massive units were designed to power the railway's flagship Chessie Streamliner. On paper, the concept was brilliant. A traditional coal boiler drove a Westinghouse steam turbine, which spun generators to power 8 traction motors. This hybrid approach promised the smooth, gearless acceleration of an electric motor alongside the self-contained freedom of steam. But executing this on a single frame required a staggering scale. The M1 measured over 154 feet long and weighed 857,000 pounds, with the coal bunker at the front and the boiler at the back. In reality, this rolling power plant was a mechanical nightmare. Coal dust and water frequently shorted out the sensitive Westinghouse generators, and the turbine struggled with extreme inefficiency at lower speeds. When the passenger service was canceled in 1948, the M1 lost its purpose. After barely running in actual service and constantly clogging repair shops, all 3 units were scrapped by 1950. Steam turbine dreams completely derailed by simpler diesels. But as railroads abandoned coal-fired turbines, what happens when you try to conquer high-speed passenger travel with a radical 4-cylinder duplex design that looked like a streamlined bullet but was completely untamable on the rails? In 5th place, the Pennsylvania Railroad's T1 duplex represents the ultimate tragic peak of American steam engineering. Introduced in the 1940s to haul heavy express trains at speeds exceeding 100 miles per hour, this streamlined locomotive was designed to outperform emerging diesels. To achieve this, engineers bypassed standard design rules, splitting the driving force across two independent sets of cylinders on a single rigid frame. 52 of these 4-4-4-4 giants were built, featuring 80-inch drivers, a 300 psi boiler, and 6,000 indicated horsepower. In theory, dividing the reciprocating mass reduced track wear. In reality, the T1 was an untamed beast. Its most notorious flaw was sudden, violent wheel slip. Because the two driver sets were not mechanically linked, a sudden loss of adhesion on one set would cause the wheels to spin furiously, sometimes at 90 miles per hour, while the train was barely moving. This volatility stemmed from improper axle equalization, complex valve timing, and a lack of training for crews accustomed to conventional locomotives. As maintenance costs and safety concerns grew, the railroad announced a sweeping diesel conversion policy in 1948. The fate of the T1 was sealed, and the fleet was scrapped by the early 1960s. It proved that even the most elegant engineering theory cannot survive if it is too delicate for the harsh realities of daily service. But if a four-cylinder steam giant could slip out of control, what would happen when engineers bypassed steam entirely and bolted surplus military jet engines directly to the roof of a passenger car? The fourth locomotive on our list, the New York Central M497, known as the Black Beetle, represents the absolute peak of high-speed audacity. In the summer of 1966, engineers bypassed all standard railway conventions by bolting two surplus military General Electric J4719 turbojets directly to the roof of a lightweight Budd R DC-3 passenger rail car. On July 23, 1966, engineer Don Wetzel throttled up the twin jets on a straight 40-mile stretch of track between Toledo, Ohio, and Butler, Indiana. The modified car screamed across the rails at a documented speed of 183.68 miles per hour, setting a United States rail speed record that stands to this day. The Black Beetle was a pure experimental spectacle designed to test track stresses at extreme speeds. While it proved that conventional passenger equipment could handle high velocities, the sheer noise, fuel consumption, and safety hazards of jet propulsion made regular commercial service impossible. It remained a brilliant, one-off dead end. But if strapping jet engines to a passenger coach represents the peak of high-speed lunacy, what happens when a railroad decides to build? In third place, the EMD DDA40X, commonly called the Centennial, took a standard diesel concept and pushed it to its absolute physical limits. Union Pacific ordered 47 of these colossal machines from Electromotive Division between 1969 and 1971, seeking brute force to dominate their western main lines. Instead of a standard configuration, engineers stretched a single frame to over 98 feet to house two complete 16-cylinder prime movers. This dual-engine setup produced 6,600 horsepower, making it the largest and most powerful single-frame diesel-electric ever constructed. However, operating this giant was incredibly taxing. Concentrating two independent propulsion systems onto one chassis meant double the maintenance, double the parts, and severe frame stresses. If one engine suffered a mechanical failure, the entire unit was compromised. When the oil crises of the 1970s struck, the Centennial's massive fuel consumption became a liability. As the railroad pivoted toward linking smaller, modular locomotives to achieve high tractive effort more efficiently, the giant fleet was phased out by 1984. But if building a giant diesel-electric stretched standard frames to their breaking point, what happens when you turn a massive steam locomotive completely backward just to save its crew from suffocating in mountain tunnels? In second place, Southern Pacific turned the entire physical blueprint of steam power completely on its head. On the grueling Donner Pass route through the Sierra Nevada mountains, crews faced a deadly hazard: dozens of miles of tight tunnels and wooden snow sheds. As massive conventional locomotives crawled uphill, toxic exhaust and extreme heat trapped in these dark passageways routinely choked crews, sometimes leaving them unconscious at the controls. To solve this literal life-or-death crisis, engineers realized they had to put the crew ahead of the smoke. Working with Baldwin, the railroad flipped the locomotive, placing the cab at the very front and the boiler behind it. Since coal could not be easily shoveled across such a distance, these cab forwards ran on pressurized fuel oil, piped all the way from the tender along the side of the boiler. The final evolution of this class, the massive AC-12 built during World War II, weighed over 1 million pounds with its tender and put out more than 124,000 pounds of tractive effort. It gave crews a clear view of the track and, more importantly, clean air to breathe. Unlike many radical experiments, this bold inversion was a triumphant success, hauling vital freight over the mountains for decades until dieselization swept the steam era away. But if turning a steam giant backward solved a mountain crisis, what happens when you discard coal, water, and traditional pistons entirely to build an ear-splitting, fuel-guzzling monster powered by a military aircraft turbine? And finally, in first place, the Union Pacific gas turbine electric locomotives, famously known as the Big Blows, pushed the limits of single-unit horsepower to the absolute edge. In the late 1950s, Union Pacific needed concentrated tractive power to haul heavy freight across the steep grades of Utah and Wyoming. Working with General Electric, they built a fleet of 30 massive 3-unit giants rated at 8,500 horsepower. This was not a standard design. The first unit housed the control cab and an auxiliary diesel engine. The second carried the massive gas turbine itself, and the third was a giant heated fuel tender. The turbine ran on Bunker C heavy fuel oil, a thick, tar-like byproduct that had to be heated to over 200 degrees Fahrenheit just to flow. When operating at full throttle, the turbine compressed air and burned fuel at an astonishing rate, emitting a deafening, jet-like scream that could be heard miles away. This raw power gave the Big Blows immense pulling authority, allowing them to drag heavy consists over mountain passes with ease. Yet, their insatiable appetite for fuel became their downfall. The turbine consumed nearly as much fuel idling as it did at full load, and when oil prices rose in the late 1960s, the economic advantage evaporated. Combined with the extreme heat, high maintenance requirements, and severe noise complaints, Union Pacific retired the entire fleet by 1970. Looking back at these 10 legendary machines, it becomes clear that the history of locomotive design is not just a story of steady progress, but a series of bold, sometimes chaotic leaps. When standard rules failed to deliver the speed, power, or efficiency railroads demanded, engineers were willing to risk everything on radical designs. These rule breakers prove that even the most brilliant failures help map the boundaries of what is possible. If you want to explore more forgotten histories of the rails, subscribe now. Across all 10 rule breakers, one clear pattern emerges. True innovation demands the courage to fail spectacularly. These machines weren't design errors, but necessary experiments that mapped the absolute limits of physical and mechanical possibility. By daring to defy convention, they forged the boundaries of modern rail transit. If you enjoyed this journey into engineering history, please subscribe for more.